I to discuss about John's lemma. So let's start. Let P be a partially ordered set that satisfies the following two properties, where first property is that P is non-empty, and second property is that every chain in P has an upper bound in P, then P has at least one maximal. So this is the John's lemma, that if P is non-empty, then every chain in P has an upper bound in P, then P has at least one maximal element. So we take an example to understand this lemma. Let's take an example. Every vector space has a basis. So we know that every vector space has a basis, but through John's lemma we will try to prove that every vector space has a basis. Let B is a non-empty set and P be the set consisting of all linearly independent subsets of V. So we are taking that P be the set of consisting of all linearly independent subsets of V. Now we take a chain T in P such that T is a subset of P. So we are taking a chain T in P which is a subset of P that is totally ordered. So T is now totally ordered subset of P. We assume that T is non-empty. So take T is non-empty. We need to show that T has an upper bound. So what we have to show that T has an upper bound. To fulfill that P has an upper bound of the John's lemma, so we'll try to prove that T has an upper bound. So that is, there exists a linearly independent subset B of V containing all members of T. So we have to just prove that there must exist a linearly independent subset B of V containing all members of T. So for that we take B is the union of all the sets, all the sets of in T. So if there are all the sets belonging in T and their union makes the subset B. So we wish to show that B is upper bound for T in P. So we have to show that B is the upper bound for T in P. So what we have to what we will have to prove that just we have to it suffices to show that B is linearly independent subset of V. And if we show that B is the linearly independent subset of V, we can show that B is the upper bound for T in P. So let's see. We assume that B is not linearly independent. Linearly independent. So we assume first that B is not linearly independent. Then there exist vectors V1, V2 up to Vk belonging to B and scalars A1, A2 up to Ak, not all 0, since they are linearly now dependent. we have taken that B is now linearly dependent. So this scalars a1 a2 up to ak not all 0, such that a1 v1 plus a2 v2 plus dot up to ak vk equal to 0 vector. So since B is the union of all sets in T, these are some there are some sets S1 S2 dot up to Sk belongs to T, such that Vi belongs to Si for every I which ranges from 1 to k. As T is totally ordered, one of the sets S1 S2 up to Sk must contain the others. The T is totally ordered, so one of the sets from S1 S2 up to Sk must contain the other sets in T. So there is some set Si that contains all of V, contains all of V1 V2 up to Vk. Vk means there are some Si we must have which contains all of V1 V2 up to Vk. So this tells us that there is a linearly dependent set of vectors in Si, but we have taken that as all the sets in Si are linearly independent, which contradicting that we have taken linearly independent sets in Si sets in P. So this cannot be true. So B must be linearly independent subsets. And this is written here that because it is a member of P, so Si must be linearly set of linearly independent sets. So by John's lemma, there is a maximal element in P. So it proves that B is linearly independent and B has an upper bound. So by John's lemma, there must be a maximal element in P and a maximal linearly independent subset B of V. So we have found the maximal element which is B of V. So this maximal element so now if there must have a maximal element B of V, so we have to show that now that B is indeed a basis of V, which we have to prove that B is the basis of V. So what remains, it suffices to show that B is a spanning set of V. B is a spanning set of V. So we assume first B is not spanning of V. So we will take first that B is not spanning of V. So then there exists some V belonging to the vector space V not covered by the span of B. So B is not spanning V, then there must exist another vector V belonging to the vector space V which is not spanned by B. So if this is true, then we will find out that B union the vector V is linearly independent subset of V. So now this spans the vector space V, but since we have already proved by John's lemma that B is the maximal element in V, which is linearly independent and which is the upper bound of all the subsets in V. So it contradicts that B union V is the linearly independent subset of V. So this is larger now, but it is not true because B is the maximal element. So it contradicts the maximality of B. So B is a spanning set of V, and this proves that B is the basis of V. So in this way we can prove that by John's lemma that every vector space have a basis. So thanks for watching.